In this video, I'll be proving that e is an irrational number. So this is the constant e, which is approximately 2.18. Okay, so let's have a look at the solution. First, we have an infinite series expression for e, which can be written as the sum of 1 over n factorial from n equals 0 to infinity. So we're going to use this infinite series expansion for e in this proof. We're going to use a proof by contradiction where we assume that e is a rational number for the sake of contradiction. And since e is greater than 0, so it's a positive number, this means we can write e as the ratio of p divided by q, where p and q are both positive integers. And we can also assume that p over q is the lowest fully simplified form for the fraction, so the greatest common divisor of p and q will be equal to 1. Now we'll have a look at the following number t over here, and we define t to equal, we have the number q here, and we'll take t equals q factorial and times it by e minus the sum of 1 over n factorial from n equals 0 to q. So you can note that the infinite expansion for e is an infinite series or infinite sum, but over here we're only summing the 1 over n factorial from n equals 0 up to q, so we don't go up to infinity here. This is an approximation for e where we stop the sum by going up to q without going onwards. Now by our assumption, we can write e as p divided by q. And if we continue, we also get q factorial times p over q is equal to p times q minus 1 factorial. And also we can put the q factorial in here, so inside the sum, so we have the sum of q factorial divided by n factorial from n equals 0 to q. So we can see that p and q are positive integers, so p times q minus 1 factorial will be an integer. And also, if we look at this term over here, since q is at least n, it means that q factorial divided by n factorial will also be an integer. So this means that the sum of all those terms, so the sum of all the q factorial divided by n factorial terms from n equals 0 to q, this will also be an integer. And so since this term over here and also this term over here is an integer, it means that t itself must be an integer. Now we'll write another expression for the number t, and we'll show how it leads to a contradiction. So you can also write t as q factorial times, and we have the number e over here. But we can use the infinite series expansion for e instead of this p over q thing for e. If we use this infinite series expansion, we get q factorial times and the sum of all the 1 over n factorials from 0 to infinity. Then you're minusing sum of the 1 over n factorials just from 0 to q. And now this is the same as taking off the first the terms up to q from this infinite series. So it's the same as doing q factorial times the sum from q plus 1 to infinity of 1 over n factorial. So we've taken off finitely many terms from this infinite series, so you're truncating the infinite series from q plus 1 onwards. And now we can rewrite this by putting the q factorial on the inside, so we have sum of q factorial divided by n factorial from q plus 1 to infinity. And now we'll use some inequalities here to get a contradiction eventually. So when n is at least q plus 1, we have q factorial divided by n factorial is equal to 1 divided by q plus 1 times q plus 2 times dot to dot up to n. And Now we'll use an inequality. So we see that q plus 2, q plus 3, and so on up to n are all at least q plus 1. So this is going to be at most q plus 1 over q plus 1 times q plus 1, and so on, and doing it n minus q times. And we also have a note that we have a strict inequality when n is at least q plus 2. So when n is at least q plus 2, then this becomes just a regular inequality sign. And we also have this thing over here is equal to 1 over q plus 1 to the power of n minus q. This means this term here, which was the value of t, it's greater than 0 because you're summing positive terms, but it's also going to be less than the sum of 1 over q plus 1 to the power of n minus q from n equals q plus 1 to infinity. And this can be rewritten, so you can change the term from n to m, where you can make m range from 1 to infinity and do q plus 1 to the power of m. This is because, for example, when n equals q plus 1, you have q plus 1 minus q equals 1, and you're continuing onwards. So you can change the variable from n to m and change where the sum is ranging from. And now we can take a 1 over q plus 1 factor out and make the sum go from m equals 0 to infinity of 1 over q plus 1 and then to the power of m. Now this allows us to use a geometric sum formula because 0 is less than 1 over q plus 1 less than 1, so this sum will converge. We have the 1 over q plus 1 here, and now using the geometric sum formula, we have 1 divided by 1 minus 1 over q plus 1. Now, if you multiply this q plus 1 into the denominator, we have 1 over q plus 1 minus 1, which is 1 over q. And this is at most 1 because q is at least 1. And since we have a less than sign over here, and this is equal to t, this means that we eventually get 0 is less than t less than 1. However, this is a contradiction because we proved earlier that t had to be an integer. So this over here, we had t had to be an integer, but we can't have an integer if t is greater than 0 and less than 1. So this gives us a final contradiction and proves that e has to be an irrational number. So you can't write e as p over q, where p and q are positive integers. Okay, so that concludes the proof of one of the proofs that e is irrational. Hope you enjoyed this video. Thanks for watching, and I'll see you next time.